Okay, chapter 4, section 2, the mean value theorem. Okay, in this section, we're going to start off by looking at something called Rolle's theorem. So Rolle's theorem. Let f be a function that satisfies the following three hypotheses. Number one, f is continuous on a closed interval from a to b. Very important that it has to be a closed interval, so the endpoints have to be part of the function or part of the domain. F is differentiable on the open interval from a to b. Okay, and three, we're going to let f of a equal to f of b. So if these three conditions are satisfied, then there is a number c in between a and b, notice not the endpoints, such that f prime of c equals to 0. Okay, so here's a few examples of how this can be achieved. Let me start off by looking at this one right here. Okay, notice that the function is, it's got solid holes at the end. It's continuous on a closed interval from a to b. The function is continuous and differentiable. So continuous already takes out the possibility that there might be a vertical asymptote, for example. Right? Prevents the possibility that our function could do something like that and shoot off to infinity, maybe come back from infinity over here and have an asymptote somewhere. Right? It's continuous, so that can't happen. And also, because it's differentiable, we're also preventing the possibility that it might have some sort of a sharp corner like this. Right? Sharp corner, not differentiable there at the corner. Okay, so we're looking at smooth functions that are continuous, differentiable, no sharp corners, nothing weird, no breaks, doesn't go off to infinity. Okay, so this is a nice stereotypical example. And for Rolle's theorem, we're also considering that the endpoints equal to each other. Notice that this height right here, whatever it is equal to f of a, but it's also equal to f of b. Okay, so all of these guys equal each other. They're all at the same height. Good. So Rolle's theorem is saying that as long as these three conditions are satisfied, that f is continuous on a closed interval. It is. It's continuous on a closed interval from a to b. That f is differentiable on the open interval. Okay, so it's continuous. So it's continuous, and we can see that it's differentiable. When we are told that a function is continuous, we knock out some of the possibilities because it's continuous, so we don't have any vertical asymptotes, but we still have to be careful about those sharp corners, right? So that's why we have to throw in that extra condition that we know it's differentiable on an open interval a to b. And we also have this extra condition that f of a equals to f of b. Okay, and so now Rolle's theorem then guarantees that there must be at least one value c such that f prime of c equals to 0. Okay, so there must be at least one. So this picture shows us how there's one. So here's the one value c, and notice that this line has a slope that's equal to 0. Right? That's what it means. So in fact, we can also just say that we'll have at least one tangent line that is horizontal. It's another way of stating Rolle's theorem. So this is f prime of c equals to 0. The slope of that tangent at that point is equal to 0. There will be at least one horizontal tangent drawn in our function. Okay, so this is just one way of drawing it. Here's a couple of other ways that we can achieve the exact same thing. Again, we have closed values there and there. Zoom in here. So here's another stereotypical kind of example. So we have this happening here. This is f of a equals to f of b right there. They're at the same height. So this function is continuous on a closed interval from a to b. It is differentiable on the interval from a to b, and f of a equals to f of b. So Rolle's theorem guarantees that there will be at least one value c. Now, from the way this is drawn here, we have a case where there's two of them. But there will be at least one value such that the slope of the line tangent to that point will be equal to 0. Another way of saying that is that the derivative evaluated at c sub 1 will be 0. And here is another case where the derivative evaluated at c sub 2 is equal to 0. Okay. Likewise, here's another example. We have a case where we have a function that is continuous on the closed interval from a to b. Here we have the case where this is f of a equals f of b. Right? They have that same height. The function is differentiable on the interval from a to b. And here it is in our picture, at least one point. Rolle's theorem guarantees that as long as all three conditions are satisfied, there is at least one point between a and b such that f prime of c equals to 0, right? One horizontal line. There's another example over here. Okay, well then there's this really obvious example. What if we just have a horizontal line like this? Right, so this function is continuous on the closed interval from a to b, and it's also differentiable. Well, the derivative is just going to be equal to 0, since this is going to be equal to some constant. Right? So this is f of a equals some f of b. Well, in this case, it's just equal to some constant. I don't know, let's call it k, constant. I would have used c for constant, but we have c's running around over here. Okay, so it's just equal to some constant values. Okay, so there is at least one place. Right, so here they just kind of pointed out a couple, such that the derivative is equal to 0. F prime of c sub 1 equals to 0. In fact, in this case, every single point is a point such that its derivative will be equal to 0. The tangent line at any one of these points is going to be horizontal. Okay, so there you have it. Rolle's theorem. If a function f satisfies these three conditions, if f is continuous on a closed interval from a to b, inclusive of the endpoints, if f is differentiable on an open interval from a to b, not including the endpoints, and if f of a equals to f of b, then there is at least one number c between a and b such that f prime of c equals to 0. Okay, but somebody more clever than me thought about this third stipulation here, that f of a equals to f of b, and they thought, well, is that really required? Do we have to make sure that the endpoints equal each other? Can we generalize it more when they don't necessarily equal each other? And what kind of a conclusion can we reach? Okay, so there's a more general rule that we're about to look at called the mean value theorem. And this Rolle's theorem is simply just one little subset, one little subcase of that larger rule that we're going to be working with. So really, we don't really work with Rolle's theorem too often. So let's move on to the more general situation. Okay, the mean value theorem. Remember, I said this is a more generalized version of Rolle's theorem. So let f be a function that satisfies the following two hypotheses now. Rolle's theorem had 3. We're going to roll it back down to just 2. Okay, so 1, f is continuous on a closed interval from a to b, just like before. 2, f is differentiable on the open interval from a to b. Good. Okay, so we got those two conditions. In Rolle's theorem, we still guaranteed, or we required, that f of a equals to f of b. But here we're not going to require that. So here's what we can conclude. Then there is a number c, at least one number c, in the interval from a to b, such that the derivative f prime evaluated at c is equal to f of b minus f of a all over a minus b. Okay, this should look familiar by now. We work with this all the time. What this is the slope of the line that connects the two endpoints of the little segment we're talking about. Okay, so let me draw something to kind of bring this together. So for example, just one little example. Let's say that we have a function that's doing this. It goes up and down and up like that. Let's say it does this. So this function is continuous on a closed interval from a to b. So let's say that this is a and this is b. Okay. So it's continuous on the interval from a to b. That takes care of one. Differentiable. Well, it's continuous, so that helps. There's no vertical asymptotes anywhere. But also, by looking at it, we can see that there's no sharp corners that would prevent us from finding a derivative. So everything is smooth and continuous. All right, we have the y, we have the x. Okay, so now what this is this. This point right here, this is going to be f of a. And this point over here, this maps over here to f of b. F of b. Right? This is the y-axis going that way. Okay, so this point right here is the point a, comma, f of a. It's that point. And this point over here is the point b, comma, f of b. So if we think about the line that connects these, so let's think about a little line segment that connects these two. Put it in green. The line that connects those two. What's the slope of that line going to be? Well, the slope of that line is going to be equal to exactly this. Right? So this part of it is the slope of the line segment connecting points a, comma, f of a and b, comma, f of b. Good. So this is saying that there is at least one value c, just at least one. Let's say it's going to be somewhere around here, just by drawing the picture. I mean, just by looking at the picture, at least one value c somewhere between a and b, such that its derivative is equal to that slope. In other words, parallel to that. So from this picture, I could see that maybe, I don't know, somewhere around here, we might have a tangent that looks like this, where that tangent is the same, it's got the same slope as this one. So that the slope of this red one is the same as the slope of that green one, right? So the slope of the red one, well, at this point, maybe I need to squeeze this over here a little bit more. So this guy comes right there, so that's C. So that point right there is the point C, comma, F of C, right there. And its slope, the slope of that tangent line, is equal to F prime of C. Good. All right, so we're saying that the slope of this tangent line is the slope is equal to the slope of this one. Therefore, this tangent line and the secant line connecting these two endpoints are parallel to each other. Now, this theorem says that there's at least one, so there might be more than one. Again, just by eyeballing this, it looks like maybe somewhere over here there might be another tangent that does that. Maybe over here. Say something like that. Ooh, that doesn't quite look right. Maybe a little closer over here. Well, something like that. So even though my picture is really messy, this is supposed to look like all three of them have the same slope. Right, so then this is going to be some f prime of c sub 2, let's say. So let's make this c sub 1, c sub 1, c sub 1, c sub 1, and then we'll say that there's some point here, c sub 2. Okay, and so the slope of this one will also be equal to the slope of the green one. So it'll be equal to this little formula here. f of b minus f of a all over b minus a. We often refer to this as well as the slope m of the line that connects a and b, so ab notation. Okay, so let's look at some other nicer examples, nicer than mine. So here's a couple of other examples of what it could look like. So here we have a function. The function itself is going to be this black one right here. This is some function f of x. And so we're saying f of x is continuous on the closed interval from a to b. You can see from the picture that it is. These solid dots right there confirm that it's continuous on the closed interval from a to b. 2, f of x is differentiable on the open interval from a to b. And we can see that it is. It's continuous, so that's almost there, but also there's no sharp corners anywhere. So that's fine. It's smooth and continuous, therefore differentiable everywhere. Good. And now if we think about the slope of the line segment that connects these 2 points, the 2 endpoints, well, that would be the slope of this blue one. Slope of blue line of, I'll just put it, the slope is equal to f of b minus f of a all over b minus a, right? That's what that slope is. And so the mean value theorem guarantees that there's going to be at least one point C, right, such that the slope of that tangent line at that point, the slope will be equal to this one. So the slope here, slope of this tangent line is f prime of C. And as we can see by the picture, they're both parallel to each other. They must have the same slope. So again, this is a confirmation of the mean value theorem that there is at least one value C that satisfies that condition, that this equals this, right? By the proof by picture here, they both have the same slope. They're both parallel to each other. Good. Here's another example, a little closer to the one I was trying to do, but this one looks nice. Again, just to confirm, this black one is the function. F of x is this black one here. And we could see that it's continuous on a closed interval from a to b. So f of x is continuous on interval from a to b, inclusive of the endpoints. Because it's continuous and there are no sharp corners everywhere, then we can satisfy the second condition. F of x is differentiable on the open interval from a to b. Good. And then again, proof by picture here, we could see that there is at least one, there's in fact two, according to this picture, 2 points such that the slope of the tangent lines at those points, those slopes are equal to the slope of the line segment that connects the 2 endpoints of your function, starting at this point and going out to that point. Okay. So this point here should have a height of f of a. This point up here should have a height of f of b. And so this line segment there should have a slope equal to f of b minus f of a all over b minus a. Good. And proof by picture, I can see that all 3 of these lines are parallel to each other. Parallel lines have the same slope. Therefore, the slope of these 2 must be the same as that one. So proof by picture here, I can see that f prime of c sub 1 is equal to f prime of c sub 2, and they both equal to the slope of that blue one, which is this f of b minus f of a all over b minus a. Okay, and then there's an alternate form of this. It's a more popular way of representing the mean value theorem, which is this one here. And then all we have to do to get this alternate form is to multiply both sides of this equal sign by the denominator. And so if we have f prime of c equal to f of b minus f of a all over b minus a, then all we have to do is multiply both sides of the equal sign by this b minus a, multiply this side by b minus a, and so we end up reducing that, and so b minus a, f of b minus f of a is equal to the product of f prime of c times b minus a, right? They just kind of flipped it around, and that's how we get this term right here. Okay, so that's really the main idea, the main concept in this section. So let's just jump into some examples and see how we can use Rolle's theorem or means value theorem to solve some of your homework exercises. Okay, so here are the exercises for this section. 1 and 2, they give you this nice graph. 1, 2, 3. So we have a graph. Verify that G satisfied the hypothesis of the mean value theorem on the interval from 0 to 8. Estimate the values of C. Okay, so I think you can probably do that. How about something like number 6? Verify that the function satisfies the 3 hypotheses of Rolle's theorem and find the values of C. Okay, so let's do number 6. Okay, verify that the function satisfies the 3 hypotheses of Rolle's theorem on the given interval, then find all C that satisfy the conclusion of Rolle's theorem. Okay, so first of all, note that we're dealing with a polynomial. Number 1, note f of x is a polynomial. Polynomials are known to be continuous, smooth and continuous on all real numbers, and also differentiable on all real numbers. So part 1 and 2 of Rolle's theorem can easily be assumed to be true just by identifying it as a polynomial. So thus, f is a polynomial. All polynomials are continuous, differentiable. On all real numbers. So from negative infinity to positive infinity. Well, then it's definitely true that f of x is continuous and differentiable. So f of x, just to go in order, I guess, number 1. So number 1 from Rolle's theorem, f of x is continuous on the closed interval from -2 to 2, right? Because it's continuous and differentiable everywhere. So it's continuous on the interval from -2 to 2. Part 2, f of x is differentiable on the interval from -2 to 2. Well, again, it's a polynomial, and polynomials are continuous and differentiable everywhere. Okay, part 3, okay, that takes a little bit more work. We need to confirm that the outputs are the same, so we're going to have to evaluate this polynomial at both of these values. Let me make some space over here. So we need to evaluate f of blank equals to blank cubed minus 2 times blank squared minus 4 times blank plus 2. So let's start with that -2. At -2, -2 there, -2 there, -2 there, we get -2 to the third power. That's going to be -8. That's going to be 4 times 2 makes it 8. That's going to be another -8. And then that's going to be +8 plus 2. So these two cancel out. and I end up with negative 8 plus 2, which gives me just negative 6. F of negative 2 equals to negative 6. Okay, so now we have to check at positive 2. F of blank equals to blank cubed minus 2 times blank squared minus 4 times blank plus 2. And so now we're going to test positive 2. Positive 2 there, positive 2 there, positive 2 there. This becomes 8 minus 8 minus 8 plus 2. So now in this case, the first two cancel out. Here the middle two canceled out. Here this and this cancel out, and I'm still left with negative 6 equals to negative 6 f of 2. So we've established that number 3, f of negative 2 equals to f of positive 2. Okay, so all three conditions of Rolle's theorem have been satisfied. So now the conclusion. The conclusion is that there must be at least one value between a and b, so between negative 2 and positive 2, such that its derivative will be equal to 0. Okay, so let's find it. To find it, well, we're going to have to take the derivative, right? So let's come back over here and say that that must mean that f prime of x is equal to the derivative with respect to x of our function, which is x cubed minus 2x squared minus 4x plus 2. Okay, zoom into here a little bit. I need to find this derivative. That's easy. That's going to be equal to 3x squared minus 4x minus 4 plus 0. And so we need to find the values that equal to 0 on the interval from negative 2 to 2. So let's set it equal to 0. Set 3x squared minus 4x minus 4. Well, actually, let's write it this way just to make sure. We need to find all c such that f prime of c equals to 0. Find all values that give you a 0, and also that c has to be in the interval between negative 2 and 2. So f prime of c, well, that's going to be 3c squared minus 4c minus 4. And we want to figure out when that's equal to 0, so let's set it equal to 0. 3c squared minus 4c minus 4 equals to 0. Let's see if we can factor this guy. The numbers are easy enough to try the guess and check method. So that would be 3c there and 1c there. And there's only a couple of ways to get a 4. You can have a 1 and a 4, or a 2 and a 2. Let's just kind of try a couple of things here. Let's try the 2. That would make it 4. This would make it 6 and 2. That would work out. So I would need plus 2 minus. Right, so I'm just kind of guessing different combinations. Minus here, plus there, just trying out different things. And after a little bit of guessing and checking, this seems to work out. This times this would give me 3c squared minus 6c plus 2c. That would give me that minus 4c, and then minus 4. Good. Next, we set each one of these equal to 0. We get 3c plus 2 equals 0. Therefore, 3c equals to minus 2. And so for c equals to negative 2/3. That's one option. And the other one is that c minus 2 equals to 0. Therefore, c equals to 2. Okay, so those are the two solutions here. Let's zoom out over here. Those are the two solutions from here. But remember, Rolle's theorem said that we needed to be inside the interval from negative 2 to 2, not the closed interval. Right? There must be at least one value c in the interval between a and b, not including of the endpoints, such that f prime of c equals to 0. So note that negative 2/3 is a member of the interval from negative 2 to 2, but positive 2 is not a member. 2 is not a member of the interval from negative 2 to 2, right? We're not including the endpoints, right? We're not including the endpoints, so it's not a member of that. So this doesn't qualify as a proper conclusion from Rolle's theorem. So according to Rolle's theorem, we found our answer, and C equals to negative 2/3 is our only answer. Okay, so let's write a nice little sentence. Thus, C equal to negative 2/3 is the only value that satisfies the conclusion of Rolle's theorem. Okay, so that's our only answer. Positive 2 is not an answer. Good. Okay, let's try another one. All right, let's try a couple more. We worked with Rolle's theorem. Let's work with the mean value theorem. How about something like number 12? Verify that the function satisfies the hypotheses of the mean value theorem on the given interval. Then find the numbers C that satisfy the conclusions of the mean value theorem. Okay, so let's work on number 12. Okay, so number 12, verify that the function satisfies the hypotheses of the mean value theorem on the given interval, then find the numbers C that satisfy the conclusions of the mean value theorem. Okay, so the conditions are actually quite simple, and again, we have a polynomial here, so all I have to do is say, note that f of x is a polynomial, and as such, polynomials are continuous and differentiable, right? All polynomials are continuous and differentiable on all real numbers, from negative infinity to positive infinity. So that makes this pretty easy. So number one, the mean value theorem, f of x is continuous on the closed interval from negative 2 to 2. And number two, f of x is differentiable on the interval from negative 2 to 2, right? Because it's continuous and differentiable on all real numbers. So those two conditions are really easy. Remember, Rolle's theorem had this other condition of making sure that f of a is equal to f of b. We don't have to have that here. Okay, so those two conditions are satisfied. So by the mean value theorem, there must be at least one c. There must be at least one c such that f prime of c equals to f of b. Well, in this case, the b is, I'm just going to put it in terms of this particular question. F of b is going to be 2, f of b all over blank minus blank. So I'll say 2 minus 2, and then 2 minus 2. Okay, so there's at least one c that satisfies this. Okay, well, let's actually evaluate f of 2 and f of negative 2 so that we can simplify what this is, and then we can take the derivative of this function and set it equal to that so we can find the value of c or values of c that satisfy this condition. Okay, so let's evaluate this polynomial at 2 and at negative 2. So I'm going to come off to the side here and do a little side work here. So f of blank equals to blank cubed minus 3 times blank plus 2. So let's try evaluating it at positive 2. Positive 2, positive 2, positive 2. So that means that f of 2 will be equal to 8 minus 6 plus 2, which means that f of 2 equals to positive 4. Minus 2 plus 2, positive 4. Okay, we got that answer. About f of blank equals to blank cubed minus 3 times blank plus 2. And now let's try that negative 2. Negative 2, negative 2, and negative 2. So f of negative 2 is going to be equal to negative 8 plus 6 plus 2, which gives me a 0. F of negative 2 equals to 0. Okay, so that means that coming back over here, I can replace each one of these. So f of 2, well, that's just going to be this 4. And f of negative 2, well, that was this 0. And so this is going to be equal to 4 minus 0, 4 minus 0, 4 minus 0, all over 4, which the whole thing just equals to 1. Okay, so given this equation, this particular equation, on this closed interval, we're saying that there is at least one value c somewhere between negative 2 and 2, such that its derivative will be equal to positive 1. Okay, so let's find that c value. Okay, so next we got to find the derivative of this function. So let's come back over here and say, okay, well, let's find the derivative. So f prime of, sorry, not c, f prime of x is going to be equal to the derivative with respect to x of that function, x cubed minus 3x squared, 3x plus 2. Well, that's a very easy derivative. That's just going to be equal to 3x squared minus 3. Prime of x is equal to this. And so now we're trying to find a c value that makes this be true. So here's the derivative. Okay, so now we want to say find all c values such that the f prime of c equals to 1. So f prime of c means we just evaluate this at c. F prime of c is equal to 3c squared minus 3. And we're going to set that equal to 1 and solve. So we add 3 to both sides. We get 3c squared equals to 4. Add 1 plus 1 plus, plus 3 plus 3 plus 3, they add up to 4. Divide both sides by 3, we get c squared equals to 4/3. And so c equals to plus or minus the square root of 4/3. Square root of 4 is 2, so we have c equals to plus or minus 2 root 3. And then rationalizing it, we'll get that c equals to plus or minus 2 root 3 over 3. Over 3. Okay, so now we get our calculator and confirm that both of these guys are within our interval between negative 2 and 2. So let's get our calculator. And it's 4 divided by 3, 4 divided by 3. Enter, and then we want to raise that to the 0.5 power, and so it's plus or minus this 1.1547. Plus or minus. Okay, so there are 2 points, and both of them, note that both of them are in the interval between negative 2 and 2, so they're both going to be valid. Right? So by the mean value theorem, we found 2 points that satisfy the mean value theorem. So thus, both c equal to plus and minus 2 root 3 over 3. Both of those points satisfy the mean value theorem. Let's confirm it with Desmos. Okay, so here in Desmos, I type in my equation that we're working with. Here it is. It's a polynomial, so we can see that it's continuous everywhere. But we're just really interested in this part right here, so I'm just going to zoom into this. And we were interested in the segment between -2 and 2 inclusive, so I'm just going to work with that. So I'm going to put this and less than or equal to, oops, -2 less than or equal to x less than or equal to 2. Okay, so now it's restricted that little portion. And the mean theorem talks about the slope of the line that connects the two endpoints. So I want to connect these two. I know it goes through this point here, and we did some work, we found that the slope was 1. So slope of 1 and goes through the point 0, 2 means that it's going to have the equation y equals to 1 times x plus 2. So there it is. Let me change the color to green. Done. And again, I want to restrict it from -2 to +2. So this, and then from -2 less than or equal to x less than or equal to +2. There we go. Okay, so then we want to know that there is at least 1 point by the mean value theorem, and we found 2, such that the derivative at those points was equal to the slope of this one, which means that the tangents at those points are going to be parallel to this one. So let's look at the tangents. So that would be the equation y equals to f prime of a prime of a x minus a, a is a slider, plus f of a and let's put it in red. And let's identify the points a comma f of a. Okay, so here we see the various tangent lines going around, and we could see that there's a couple of places where it seems, at least by the graph, somewhere near there, this line is going to be parallel to that one. They're going to have the same slope. And somewhere over here, there's going to be another one. Somewhere around there, there's going to be another place where this line is going to be parallel to that one. Okay. Well, we found that it was at the points when x was equal to square root of 4 over 3. So let's graph this point with that value. Copy, put it over here, Control B. And let's replace the a with just that root 4 over 3, square root of 4 divided by 3, square root of 4 divided by 3, finally, square root of 4 divided by 3. And let's put it in red. this guy. And there we go. So this is one of them. At x equals to square root of 4/3, we see that this is exactly what we're looking for. The tangent line is parallel to the secant that connects the two endpoints. And there was another one at negative, right? So let's copy this. Copy, put it over here, except this time everything's negative. So negative there. And negative out here means that this is going to turn positive, plus, and then f of negative there. And so we get another one. Let's put it in red again. Okay, so we found the 2 points there and there. Now, I'm not sure why being rounded a little bit different. Oh, that's this thing. Okay, so let's graph those dots. So that would be that dot there, and here there would be this dot there. Okay, so we found what we were looking for. And also note that if I wanted to find the derivative of these 2 points, Desmos can just find it for me, so that's nice and convenient. I can just say find the value of the derivative at that point. It calculates it for me right there. It's a 1. What about the other one? We have f prime parentheses of positive. Positive or negative, they both give you the same result. The derivative is 1. We know that the slope of this green line is a 1. We know that the slope of these 2 tangent points is going to be 1. The derivative evaluated at those 2 input values is 1. So it satisfies the mean value theorem. Okay, let's move on. Okay, let's try one more. Very similar, except finally let's look at something that's not a polynomial. So number 14, 1 over x. Verify that the function satisfies the hypotheses of the mean value theorem on the given interval. Then find the number c that satisfies the conclusions of the mean value theorem. Okay, so on the graph 1 over c, remember that this is one of our standard functions, and its graph looks a little like this. X, y. And the graph is going to have a vertical asymptote at the y-axis. And it comes out this way like that. Okay, so we know that this function f of x is continuous everywhere. So 1 over x is continuous and differentiable everywhere except x equals to 0. So it's differentiable, continuous and differentiable on the interval from between negative infinity to 0, not including 0, unioned with 0 all the way out to positive infinity. So part 1 of our mean value theorem is easily satisfied. Well, really part 1 and part 2, because we're only interested in the segment between 1 and 3. So here's 1, here is 3, and we're only interested in this little segment from there to there. And in that little segment, the function is continuous and it's differentiable. Okay, so clearly, f of x is continuous on the interval between 1 and 3 inclusive. And number 2, f of x is differentiable on the interval between 1 and 3, not including the endpoints. Okay, so because that's true, then the mean value theorem guarantees that there must be at least one value c somewhere in here. There's at least one value c, such that f of c is equal to f prime of c is going to be equal to f of 3 in this case minus f of 1 in this case divided by 3 minus 1. This is equal to f of 3 is equal to 1/3 minus f of 1 is equal to 1 over 1 divided by 3 minus 1, which then gives me 1/3. We're going to common denominator. Let's multiply this by 3 over 3. That's going to give me 1 minus 3 over 3 all over 2, which gives me negative 2 thirds in the numerator times the reciprocal of the denominator. So let's go ahead and think about this as one fraction there, another little fraction here, multiply the numerator, which is negative 2 over 3, times the reciprocal of the denominator, which is going to be a 1/2. The 2's cancel, and so I'm just left with 1/3, negative 1/3. Okay, so according to the mean value theorem, there must be at least one value c such that f prime of c equals to negative 1/3. Let's find that derivative then. F prime of x is going to be equal to the derivative with respect to x of 1 over x, which we know is the same thing as the derivative with respect to x of x to the negative 1 power. And so now that we can find pretty easily using our power rule. That means that f prime of x is going to be equal to negative 1 times x to the negative 1 minus 1. Means f prime of x is equal to negative 1 over x squared. Okay, so find all c values such that f prime of c equals to negative 1/3. So that means that negative 1 over c squared, that's what f prime of c is, replacing a c and a c there, must be equal to negative 1/3. So multiplying and solving for this, we get c squared must be equal to, well, 3, right? Kind of cross multiply, cancel out the ones, we get this. And so that must mean that c equals to plus or minus root 3. Remember that we're only interested in the interval between 1 and 3. Okay, so we're only interested in values in the interval between 1 and 3. So I'll come up here, note that negative root 3 is not a member of the interval between 1 and 3. So thus, c equal to positive root 3 is the only thus c equals to positive root 3 is the only value that satisfies the mean value theorem. Okay, so let's verify this with Desmos, but in order to do that, I want to find the equation of the line that connects the two endpoints of the segment we're interested in. So if I'm interested in the line that connects these 2 points, and I want to find the equation of that line, well, first of all, we already found the slope. That equation of the line that connects it has this slope, m equals to negative 1/3. And I also know that it goes through this point, which is going to be the point 1 comma 1 over 1, or just 1. So we have the point 1 comma 1. And so if I find that equation, it's going to be y equals to mx plus b. The m is negative 1/3, so y equals to negative 1/3 x plus b. If I use this as my x and y, I can get that y equals to negative 1/3 times 1 plus b. And so if I add 1/3 to both sides, I get 1 plus 1/3 equals to b, or 4/3 equals b. So I can get that equation is going to be equal to y equals to negative 1/3 x plus 4/3. Okay, so that's the equation of the line segment that connects the two endpoints of the region we're interested in. Just to kind of draw that again, kind of zoomed in a little bit more, we have this portion that looks like that. This is a portion of the bigger graph of 1 over x. And there's going to be a line segment that connects these two values there. And we found out that the equation of that green line is right there. The slope is negative 1/3. And so we also discovered that there is a point C somewhere here, C equals to √3, such that f prime of C equals to the slope of this green line, which we said was equal to negative 1/3. So we'll see that it kind of gives you a tangent line that looks something like that. Okay, let's use Desmos to do a better job of drawing this picture than I did. Let's go to Desmos. Okay, so here's the graph of 1 over x, right? Standard 1 over x function, and its domain is all real numbers except 0, as we know. And we're only interested in the segment between 1 and 3. So let's zoom into here. Really zoomed in, okay? So between 1, really zoomed in, right? So between 1 and 3. Let's restrict it so that it only shows that part of it. There. So now it got rid of the rest of the graph, and now it's just focusing on that little portion of it. Okay, well, we did some work and we figured out that this is the equation of the line segment that connects the two endpoints. So just connect them. See, that's that line segment. It's got this equation. This green one has the slope of negative 1/3. Good. And then if we think about the tangent lines, let's see. Here are all the tangent lines to the original 1 over x function just in this little segment. And we can see that there's going to be really exactly one point where the tangent red line is going to be parallel to that green one. Not there, not there, somewhere around there that's going to be it. And we discovered that the answer is going to be at the point where x equals to √3. So let me erase this guy here. This guy and this guy, and here it is. Here's the equation of that guy, and in fact, let's graph it. It's going to be graph the point √3 comma f of √3. Label it. There it is. So this is 3, and it's going to be parallel to that. And we can confirm that at that point, the slope of the red one is negative 1/3. Just like we had already confirmed that the slope of the green segment that connects our two endpoints, there and there, there and there, 3 comma 1/3 and 1 comma 1, the slope of that one was equal to negative 1/3. Okay. So hopefully that makes sense. Okay, let's take a look at number 26. Okay, suppose that the first derivative of x is greater than or equal to 3 but less than or equal to 5 for all values of x. Show that 18 is less than or equal to f of 8 minus f of 2 less than or equal to 30. Okay, a lot of information is packed into this initial statement right here. Suppose that this first derivative is trapped between 3 and 5 for all values of x. By that statement, we can conclude that the derivative exists for all x, and its output is somewhere between these two values, right? So from that statement, we can conclude that f of x is differentiable for all values of x. So on the interval between negative infinity to positive infinity, right? That's a good assumption there because the derivative exists everywhere for all values of x. And in addition to that, that derivative happens to be trapped between these two values. If f of x is differential everywhere, well, okay, now I'm going to focus my attention on this, right? This is what they're asking me about. So I'm just going to say, well, in particular, if f of x is differentiable on negative infinity to infinity, then easily we can conclude that f is, I'm going to do this one first, f of x is differentiable Differentiable implies continuous, right? If you know something is differentiable, you know it's continuous. The other way around is not true. If you know something is continuous, you don't necessarily know that it's differentiable because of the possibility of those sharp corners. But if something is known to be differentiable, then it is known to be continuous. So we can use the same little statement to satisfy both conditions of the mean value theorem. F of x is continuous on, and let's just throw in the 2, 8, because that's the one that we're interested in, and so differentiable on 2, 8. So the two conditions of the mean value theorem are satisfied. Thus, there must be at least one value c. Thus, there must be at least one value c such that f prime of c equals to f of b, which is in this case an 8, minus f of 2 all over 8 minus 2. Right? That's why I became interested in this interval from 2 to 8, because I could see that that's what they're interested in over here. So I can simplify this a little bit and say that this must mean that f prime of c must be equal to f of 8 minus f of 2 divided by 6. And so now if I multiply both sides by 6, I'll get that 6 times f prime of c equals to f of 8 minus f of 2. Okay, almost there. Now let's come back up to this statement that they gave me. We were given that 3 is less than or equal to f prime of x less than or equal to 5. Okay, and of course c is a value somewhere between 2 and 8, so it's one of these values. For any value x, f prime of x is between 3 and c, and for any value x, f prime of x is between 3 and 5, so that must mean that 3 is less than or equal to f prime of c less than or equal to 5, right? This is saying for any x, this is true. Well, c is one of those values. It's a value between 2 and 8, so it's got to be true that this is the case. And so now if we multiply everything by 6, we'll get that 3 less than or equal to f prime of c less than or equal to 5. So we're going to multiply this side by, we're going to multiply this side by 6, multiply this by 6, multiply that side by 6. Then we'll end up with 18 is less than or equal to 6 times f prime of c less than or equal to 30. And, well, we established that 6 times f prime of c is this difference. So we have that 18 is less than or equal to f of 8 minus f of 2, which is less than or equal to 30. And that's what they wanted you to show. So we're done. Okay, so they're all a little tricky. This is a tricky section. Hopefully I've given you enough to get started. So please work on your homework. And as usual, if you have any questions on anything, please come by to my office hours. I'd be glad to go over any one of these questions.
Do your homework.